Okay, today we will discuss about the time domain filters, which are used for filtering the various noise or artifacts in biomedical signals, especially in the ECG signal. Okay, so there are various sources of noise in the biomedical signals that we have discussed. Okay, so you may get high frequency noise due to instrumentation amplifiers or due to this electromagnetic waves or due to the thermal noise or power line interference. Okay, so then you may have a low frequency noise such as baseline wonder. The frequency of this is very less, it is generally below 1 hertz. Okay, and it causes the baseline of the signal to drift. So you have a signal like this, like this. So this is a baseline drift, okay, which basically occurs due to this respiration or the movement of the chest electrodes or coughing and so on. Okay. So the low frequency and the high frequency noises, these are the two fundamental noise sources in the biomedical signals. Okay. So the problem is now we have to provide a potential solution to the problems. Okay. So we will first uh, tackle this high frequency noise, but how you can remove it. One method to remove this high frequency or the random noise is synchronized averaging. Okay, so in this we assume that what we do in the synchronized averaging, if you have the multiple realizations of the same signal, okay, so let us suppose you have a clean signal x of n and it is corrupted with some random noise zeta n, okay, and you generate a noisy sequence y. Okay, xn is the noise free signal and this is your noise. So they are added together to generate this noisy signal. So the problem is to estimate now this signal from y of n. Okay. And for synchronized averaging, we assume that we have the multiple copies of the same process or the same realization. It means you can use the index here a k. If k may be from 1 to n sub to suppose m. Okay, so you have n copies of the same measurement. Okay, it means okay, you measure the signal. Suppose you measure n samples, you measure it up to some time t, and depending upon the sampling rate, suppose you have n samples. Okay, so you measure at one instant, you get a signal y1 having n samples, which is a superposition of the original signal with the random noise. Okay, and x, of course, this is x1n. Okay, then you measure the same signal another time, so you get y2n. So it is again x2n plus theta 2n and so on. So you have the multiple copies of the same signals measured at different intervals of time. Okay. So in the synchronized averaging, the basic concept is that if you simply add all these copies together, yk and k from 1 to n, and we assume that this noise is a zero mean random process, zero mean noise with a variance of sigma and square. So as you go on adding these signals, and if you assume that okay, this the original information it remains same. Okay, if the original signal it remains same, so every time you change this, you measure this signal, your noise will be different. Okay, so if you go on adding these multiple copies of all these measurements, what you will left with that this signal will be basically added m times. So it is x1n here, x1n is also your x of n, x2n is also xn. So it is basically m times xn if you multiply, if you add m copies. And since this is random noise, so as you go on increasing the copies of the signal, it means as m increases, so the sum of all these noises that turns towards to zero. This is how you can eliminate the random noise from the signal if you have the multiple realizations or multiple copies of the measurement. Okay, so you can improve the signal to noise ratio using synchronized averaging. But in the synchronized averaging, there is one thing that all these signals they must be aligned together. Okay, so if you have a suppose ECG signal, let us suppose. So this is original signal and it gets corrupted by some random noise, and so on. This is one copy. Then you again measure the signal. So we assume okay that the signal is same, only noise is changing. Since it is a random noise, so the noise will be different in this case, and so on. Okay, so if you add all these copies together, what you will left at the output is a ECG signal, which will have very less, you can say, amount of noise in it. Okay, because the noise will cancel each other. The signals will be simply added together, but the signals will be added only if they are aligned. It means you have to find the QRS complexes. Suppose this is a R peak in this segment, and then there's a R peak in this segment, or even another one, suppose one other. So what we have to do, we have to find the R peaks. So the R peak of this is not aligned with the R peak of this. Okay, so you have to find the R peaks in these two segments and the R peaks. So they must be time shifted or they must be aligned with each other. Then only this synchronized averaging will work. Okay, the alignment is very important. So for ECG signal, the QRS complexes they must be aligned. Okay, this is how you can remove the noise if you apply synchronized averaging by alignment of different templates in this ECG signal. Okay, so the more number of templates you are going to add, the more clean signal you will get at the output. Okay, and let me show you one example. See, this is a ECG signal with random noise. Okay, this is shown as cycle number 3. It means the third measurement. Then you again measurement after some time. This is the fifth measurement. ECG cycle number 5. Okay. Similarly, you have cycle 1, cycle 2, up to suppose 11 cycles are there. Okay, only 2 cycles are shown here. Cycle number 5 and cycle number 3. And if you simply add them together, what you will get an average of 11 cycles, which is a clean ECG signal. Okay, the random noise is basically cancelled from the signal if you had multiple copies of the same process, which is measured at different intervals of times. Okay, this is how synchronized averaging works. Okay, but so what we do in the synchronized averaging, we measure a signal at repeated intervals of time. So you have different copies of the same measurement. Okay, and if the noise is a random noise, it is zero mean noise, and if you add all those multiple copies by aligning these different segments, output will be a noise free signal. Okay, but say practically you have single realization or a single measurement. Okay, so a single realization or a single measurement, and if that is corrupted by some noise, in that case, how can you eliminate this noise from the signal? So we use in that case moving average filters. Okay, when you have only one signal at hand. Okay, so suppose you have a signal and this signal is gets corrupted by some random noise, high frequency noise. Okay, so how to eliminate this noise from this signal when you have only one measurement or one signal available with you? So we use moving average filters. Now see, the concept is again the same, that you have to perform some sort of averaging to cancel this random noise. Okay. So initially, if you have multiple copies of the same signal, you have one process, another realizations, another realizations. So okay, so you go on adding these realizations, so the random noise gets cancelled, you get a clean signal at the output. Okay. But if you have only one signal with you, which is corrupted by the random noise now, and you have to remove this noise from the signal. So you, in place of having different copies and going on adding these copies, you have to find a average along the time axis basically. Okay, so you have to find a filter, averaging filter, which averages the samples of this noise and it moves ahead in time. Okay, so what is moving average filter? Or mathematically, it is basically nothing but a FIR filter. You can simply say yn is equal to bk x of n minus k from 0 to n. So you have a signal and these bk or these filter coefficients. So k0 to n means you have n plus 1 samples. Okay, it means suppose you start at any time n. This is a signal, and if you generate the output signal from this is input sequence xn. So how you generate this output sequence yn? For any particular instant of time, what will be my output? Suppose I take output here. So x of n minus 1, n minus 2 up to n minus m, the previous n plus 1 samples, they are multiplied with the filter coefficients and added together. Okay. Or 1 by n you can write here, 1 by n plus 1 also, because it is average. Okay. Or this factor you can already incorporate in the bk itself to get this averaging. Okay. Now it means for any particular time n, suppose at this point you are computing the output. So what will be the output? So you look at the previous samples in this window. This is my filter window now, having n plus 1 samples. Okay. Starting from 0 to, you go to n x of n to x of n minus capital N. Okay. So these n samples, they are in the window. Now they are multiplied with some coefficients which are fixed, bk. And you multiply them and add them together, you get the output at this particular time n. Okay. Then at next time n, you again see the previous n samples. It means now this window is basically moving ahead by one sample. So it see only those samples which are falling within this window. And again find the multiplication with the filter weights, add them together, you get the next output. Similarly, at this point, this window will be shifted again by one. Okay. So this window is, so you have a window function. So you have a signal. When you apply this averaging filter on the signal, so what it basically is, so at a particular time n, you choose a window function And all those samples which are in this window, they get multiplied with the impulse response of the filter and added together. You get output at this particular time, suppose and not. Okay. Then at next instant, this window will be now shifted to the right. This window will be moving. This is what is called as a moving average. Okay. So it sees all now at this particular time, it can only see those samples which are within this window. So they are again get multiplied with the filter coefficients and added together and so on. This is how the moving average filters they are applied. Okay. Now one very important filter that is generally used for biomedical signal is the hand filter, or we call it as Hanning filter. Okay. What this filter is basically, the output in this filter is generated using this 1 by 4 x of n plus twice of x of n minus 1 plus x of n minus 2. Okay. So you can see what is the what are the filter options in this case, bk, which is basically the impulse response. So x of n is multiplied with 1 by 4, it means at 0 it's 1 by 4, and at n is equal to 1, x of n in this one 2, so 2 by 4 it is 1 by 2. Then again at n is equal to 2, it is again 1 by 4. So bk, the filter options are 1 by 4, 1 by 2 and 1 by 4 for Hanning filter. Okay, so it is a 3-length filter basically. So when you apply this filter on this any signal for averaging, so at a particular time n, it will just see the previous 3 samples including that sample. So this sample and this sample and this sample. So this is multiplied with 1 by 4, this is multiplied with 1 by 2, this is multiplied with 1 by 4. So they are added together. You will get the output at that particular instant of time. So at next time, this n1, now this window will move ahead. So it will now see this sample, then the previous 2 samples, this one and this one. Okay, so this gets multiplied with 1 by 4, then 1 by 2 and 1 by 4. Again add together and so on. And like this, which this window will move ahead. Okay. Now if you see this filter in the frequency domain, so what is the Z transform of this? It is 1 by 4. It is 1 plus 2Z inverse plus Z to the power minus 2. Or from this Z transform, you can find its frequency response h of e to the power j omega. So it is 1 by 4 1 plus 2 e raised to the power minus j omega plus e raised to the power minus j 2 omega. Okay. So or you can take e raised to the power minus j omega as common from this. You will get e raised to the power j omega plus 2 plus e raised to the power minus j omega. So it will become 1 by 4 e raised to the power minus j omega into 2 plus. So these two combined will become 2 cos of omega. Okay. If you divide them by 2, multiply by 2. So you'll get e raised to the power j omega plus e raised to the power minus j omega by 2 cos omega along with this factor 2. Okay. So this is the frequency response. From this you can say, okay, what is the magnitude response of this filter? It will be, you can cancel this 2 and 2, you can write it as 1 by 2 e raised to the power minus j omega into 1 plus cos of omega. So magnitude response is 1 by 2, 1 plus cos omega. And the phase response for this filter is minus of omega. So it is a linear phase filter. Okay. And if you plot its frequency response, you can easily plot it, the magnitude response. So at omega is equal to or it is, you can say, okay, it is 1 by 2 plus 1 by 2 cos omega. Okay, so if you plot this cos omega function, so at omega is equal to 0, it is 1. So then as omega goes on increasing, this will decrease. So it will have a response like this. Okay. And if you add 1 plus 2 to this, that is a constant factor, it will simply shift its base to this point, 1 by 2 plus 1. Okay, so 1, this is 1 by 2. So if you add this to this response will be shifted upwards by 1 by 2. Okay, and omega is equal to pi by 2, it will become 0 basically. Okay, something like this, cos omega. And the phases are, of course, in, so it's a low pass filter basically, if you see. So bridging filters, they basically are low pass filters. Okay, or if you see a more exact response for this, you plot it exactly. This is the magnitude and the phase response of this Hanning filter. It is called as a smoothing filter also. Okay. So from this response, what you can see, this is in dB scale. So 0 to 500, they had plotted it. Okay, it means your sampling rate is basically 1000 here, 1000 hertz. Okay, so we generally plot it from, in terms of omega, we plot it from 0 to pi by 0 to pi. Okay, and this frequency pi, it basically in the continuous or analog domain, it corresponds to this frequency of fs by 2. Okay, so that's why we have plotted it from 0 to 500. So 0 to 500 means we have sampling rate of 1000. Okay, now see, you can see that of around at a frequency of 200 hertz, this is the cutoff frequency where the gain is almost, this is 3 dB, minus 3 dB. Okay, and this 200 hertz is, if you see, for a sampling rate of 1000 hertz, this is 20%. Okay, so for 20%, up to 20% of this sampling frequency, these frequencies are basically have attenuation which is up to 3 dB. And if you see at this frequency 400 hertz, which is 40% of the sampling frequency, the attenuation is more than, beyond this frequency, the attenuation is more than 20 dB. This one. Okay, it means all these frequencies, they are highly attenuated. Okay, but see, since ECG has a frequency up to 100 hertz only. Okay, so the clinical bandwidth, it is up to 100 hertz. It means all the frequencies, they are basically passed without any much attenuation. So this is not at a sampling rate of 100 hertz. This is not a adequate filter for ECG processing. Okay, but if you change the sampling rate, if suppose you change, if you plot this using a sampling rate of 200 hertz, then this will go up to only 100 hertz. And in that case, the 20% of 200, that is up to 40 hertz. It will be around here. Okay. Or 40% of this, it will be 80 hertz. It means frequencies which are beyond 80 hertz, they are basically attenuated by more than minus 20 dB gain in that case. Okay. Of course, the plot will be different in that case. The plot will be same, but its frequency axis will be different. So this 500 will become 100. Okay. So divided by 5 basically. So if you divide this by 5, you will get 80 hertz here. So now at 80 hertz, you get attenuation of minus 20 dB. And all the frequencies beyond 80 hertz, they are suppressed by more than 20 dB. It means it will be in that case a good low pass filter for processing ACC signals. Okay. So the high frequency noise can be removed using this filter in that case, the Hamming filter. Okay. Anyhow, you can increase this the length of this window, the moving average window, to get more and more or higher attenuations. Okay. So we'll discuss in next that if you take a moving window of 8 length, then it will provide a more attenuation in the desired passband.